Hello, I'm Anthony Ward, also known as antCGi, and welcome to a new series where I explore rigging a car using Autodesk Maya. In the previous video, we worked through various options for automating wheel rotation, so next I want to demonstrate one approach to simulating tyre pressure. Now, rather than using lattice deformers, which is the traditional approach, I thought I would try something different and use a joint-based setup, which gives us much more flexibility. Before we get started, have you thought about attending AU 2023? It's the Design and Make conference taking place in November. This has always been on my radar, but seeing the lineup this year has got me excited to attend, so much so that I already have my free digital pass. Now, before I tell you more, I would like to first mention that this video has been sponsored by Autodesk, the Design and Make platform company. Autodesk is a tech leader in a number of industries, and they've completely revamped their flagship event this year. I've got to say, there are a ton of great classes on animation, visual effects, games and design visualization, as well as discussions around AI workflows in Maya, and talks about the next frontier of film and TV production. Some of the sessions I'm looking forward to include exploring Maya's workflows for character animation, reverse rigging, and Maya and ZBrush together, an intro guide for indie artists. But those are just a few. There will be so much more I'll be watching and learning from. Now don't worry, if you can't make it all the way to Las Vegas for the full event, there's a free digital pass which gives you access to live streamed and on-demand sessions, classes, talks and much more. It costs nothing to sign up, so follow the link on the screen or in the description below to secure your free pass now. So here we are, where we left off in the previous video. We can move the control and the wheel rotates. Since the last video, I've made a few changes to the scene, so the rotation is now based on a locator rather than directly driving the joint. This is just so I can keep the skeleton hierarchy separate, which isn't important unless you're building this rig for a game engine. If I make the joints visible, you will see that I have also created a series of spokes. There is an inner joint and an outer one, and these rotate with the main wheel joint. The idea is that these will scale, much like a traditional stretchy joint setup, and when they do, the tyre will compress. We can also use this to spread the tyre too. Although for a better result, you could add an extra joint here, around the middle of the tyre. I've used just 16 joint chains here, but feel free to add more if you need a more precise simulation. One other thing I wanted to mention is that with the high resolution model like this, you might find it tricky to get a good distribution of the skin weights. What I did to combat this was first skin a low resolution proxy model. You can then simply copy the weight values across using the Copy Skin Weights tool. So as you can see, you get a much nicer distribution of weights. Okay, let's hide all but one of the spokes. The process is the same for all of them, so it will be easier just to focus on one first. We can then apply the same process to all the others. We can hide the model too. And let's change the display style of the hub joint. First, let's build the stretchy joint system. We need a few locators to help with this, so create one to start us off. And let's make it bigger. We want an inner locator, outer locator, and an IK handle locator. The inner locator needs to match the position of the inner joint. And the others match the outer joint. Next, parent the inner and outer locators to the wheel rotation locator. These will track the positions of the tyre when it isn't under pressure, so they need to follow as the wheel rotates. Now we need a rotate plane IK handle just going from the inner to the outer joints. Parent that to the IK handle locator and rename it 2. Now as we rotate the wheel, the joints stay focused on the IK handle. Now let's build the stretchy network. Open the node editor and bring in the inner locator and the IK handle locator. We're using these because if we use the joints directly, we will get a cycle warning. Let's arrange these. And now we need a distance between node, so press tab and start typing the name, and when it pops up, just click on it to create it. Connect world matrix 0 from the inner locator to the node's in matrix 1 attribute, and then world matrix 0 from the IK handle locator to in matrix 2. Let's rename the node. Oh, I missed the 1 from the locator names. Now we need a multiply divide node to help calculate the stretch. Connect distance to input 1x. This is the current distance between the two locators, so we need to store this value in input 2x as the rest state. Now change the multiply divide node's operation to divide. This will then divide the stretch distance by the rest distance and give us a value we can use to drive the joint scale attribute. Let's just check. So we need the Y attribute. I'll bring the inner joint in and connect output X to scale Y. So there we can see it's connected. And if I move the wheel, the joints stretch so the end stays locked on the IK handle locator. What we need next is a way for the IK locator to be restricted with its movement, so as the wheel rotates, the end joint hits the floor and then doesn't go any further. In addition to this, it still needs to follow as the wheel rotates too. First we need a floor, so create a basic polygon plane for now, but any geometry will do. I'll scale this up. And we need to make sure we freeze the transforms too. And delete the history. Select the floor plane now, and then the outer locator. What we're going to do is use a proximity pin node, and what this will do is track the movements of the outer locator, but plot them on the floor plane. You'll get a better idea of what I mean once it's created. Go to Constrain, Proximity Pin, and open the options. We need to set input to existing transform because we're using the outer locator's position as the input. Output needs to be set to locator, and this will create a locator on the floor plane. We can leave the other settings for now. And let's just add that. We now have a pin output locator here. I'll make it bigger so we can see it. Let's change its colour too. I'm going to temporarily move the IK handle under the rotation group for now, just to demonstrate what the proximity pin has done. As I rotate the wheel, you can see the yellow pinned locator is following the outer locator, but it's staying locked onto the floor plane's surface. You'll notice that it's rotating too, so let's address that next. Let's open the pin node in the attribute editor. I'll update the name first. The first thing we need to change is the coord mode, so swap this over to UV. That fixes the rotating. I'll pin the attribute editor to keep it open. The next thing we need to check is the orientation of the surface locator. If I select it, you can see that X is pointing up and Z is aiming backwards. We need this locator to match the orientation of the outer locator, or the IK handle will flip as it switches between them. The normal axis should be set to Y, but when we try we get a warning, and this is just because it clashes with the tangent axis. So we change this first. Let's set it to Z for now. And now we can set the normal axis to Y. And finally the tangent axis to X. There are two other attributes to mention here, and those are the translation and orientation offsets. Setting rotation to 1 will make the locator copy the outer locator's orientation. The translation option adjusts the offset from the surface. We won't be using these yet, but it's good to be aware of them. I'll rename the locator before we move on. And this needs to remain outside the hierarchy too, like the IK handle locator. With all that set up now, the next step is to make the IK handle locator switch between following the surface locator and the outer locator. Now you could use a traditional constraint to do this, but we are going to use a node instead. So back to the node editor, and bring in the three main locators, so the outer, surface and IK handle. Now we need a blend matrix node. Connect world matrix 0 on the outer locator to the input matrix attribute. And now connect world matrix 0 from the surface locator to the target matrix attribute. I'll just rename the node. Now we connect output matrix to the IK handle locator's offset parent matrix attribute. Okay, there we go. If I rotate the wheel, you'll notice that the joint is following the surface locator now, so it looks like it's sticking to the floor plane. All that's happening is the joint is stretching towards the IK handle locator. What we can do now is use the weight value here to move it back to the outer locator's position. If we move the wheel down, you can start to get an idea of where we're taking this rig, because the joint stays on the floor plane. If I blend it back to the surface locator, it moves back. So we next need to add the ability to check where the locators are and automatically blend between the two. Okay, let's go back into the node editor. We want to compare when the outer locator goes underneath the surface locator, and when it does, adjust the blend matrix node to swap what the IK handle locator is following. Now we ideally need real world values for this, so first we need to convert the world matrix attributes so we can use them with a condition node. We can use a decompose matrix node for this. So connect world matrix 0 to input matrix. Create another and then do the same for the surface locator. If I open this in the attribute editor, you can see that it's taking the world matrix values and giving us a translate Y attribute, which we can use. Now we create our condition node. And connect output translate Y from the surface locator to first term, and then output translate Y from the outer locator to second term. We can then compare these two values. So we check if the first term is less than the second term, so the outer locator is lower than the surface locator. Let's find the blend matrix node and bring that into the node editor too. And we can use the output from the condition to drive the weight value. So connect outColor to weight. So if first term is less than second term, so it's true, it will output the colour if true value here. If it's not, so it's false, it will output the colour if false value below it. Let's try this now. Okay, good. The joint sticks to the floor, but is then released when it's raised above it. And it still works as the wheel rotates. Let's rename the condition node and quickly bring back the tyre. Okay, good. So as the wheel rotates, it's being pressed against the floor. The same happens if we raise and lower the wheel too. We have the main compression in and working, so let's now add in some extra features, like making the tyre spread too as it's pressed against the floor. And we can again scale the joint to do this. Back to the node editor, and bring in the outer joint this time. Let's find the scale factor node we created earlier. We can use that again here. We need another multiply divide node, so let's copy this and rename it to tread squash. Open these. Connect output X, which is the main scale value, to input 1X and input 1Z, so we can use both attributes if needed. Let's set the input values on the tread squash node to 5 for now. And then connect output X to the scale X attribute on the joint, and output Z to scale Z too. We can close this now, and we can edit the input values to adjust how much the tyre squashes. Oh, hang on, we need to set the operation to power this time. And edit it on the channel box. So we can get some squash here now too, so it spreads as it's pressed against the floor. We can adjust the scale along the Z-axis too if we like. I'll leave that one for now. So as we move the wheel now, it rotates and is compressed against the floor. That's the main system applied to a single chain, so let's take a break now and add it to the rest. Okay, here we have all the spokes rigged. And as you can see, we have lots of locators now too, so it's best to hide them away in groups. The wheel happily rotates now. And if we lower it, the tyre is pressed against the floor. Let's hide the joints. The beauty of this setup is we can also deform the floor model. And the tyre reacts correctly. Now you may get an issue when you reorientate the wheel, like this, where the joint flips. And this is why we used rotate plane IK handles, so we can easily fix it. All you need to do is make sure the pole vector attributes are set to 0. And as you can see, that's now fixed. You could also increase the offset orientation on each pin node too. So when the IK handle locator is swapping to it, it's a better match. But this is a personal preference and quite easy to do. So I just spotted that the tyre isn't rotating at the correct speed, as you can see. But with this rig I can quickly fix it by adjusting the rotate multi-attribute. There we go, that's much better and didn't take that long. It also looks like I might have mixed up my attributes earlier. We want the tread to squash along the Y and X axes instead, so I just need to update these nodes. Okay, so as a final step I've added some extra attributes here to control the tyre squash and spread. These are just connected to the Tyre squash nodes input to X and input to Y attributes on each chain. So we can basically control all the joints just with these two attributes. This just gives the animator more control over how the tyre reacts to the floor. Okay, now onto the script I mentioned at the beginning of the video. Here it is. I called it joint compression rather than tyre pressure because it can be used for so much more. So let's say we've restarted the wheel. It has the rotation and all the joints set up, but it doesn't have the tyre pressure yet. First, we input the name of the geometry the joints will collide with. And then the main control which will house the attributes. Next, we need to define which axes the joints will squash and stretch in. The stretch axis is the one pointing down the inner joint. The squash axis is the axis you want the tyre to squash along, so in this instance it's Y. Finally, the spread axis, which is X. Now I've added these options in so you can change them to suit your own rig. Once those are set, we just need to select the inner joints, not the outer ones. We can select them all and click the button to add the rig. So those are added, but we need to do one more step. The rotation locators here need to sit under the main node, which is rotating the wheel. With this particular rig, it's the wheel rotate locator here. Okay, so those all follow the wheel. And the joints collide with the floor plane. Perfect. As you can see, on the main control are two new attributes now, so you can adjust how much the tip squashes and spreads. So this script and all the files used in this series are available now at the antCGi store, and also my Cube Brush store. I'm hoping to also try and create a script to automate the wheel rotation too, and once I do, I'll update the files later. So there we go. Simulated tyre pressure using joints and proximity pin nodes. Okay, so we've got rotation and we've got tyre pressure. What I think we'll do is leave the wheel for now, and in the next video let's look at rigging the rear and front suspension. Remember to head over to autodesk.com/antCGi to grab your free digital pass to AU 2023, or find the link in the description below. So there we go. Thanks so much for watching. If you have any questions, please post them in the antCGi community Discord server. That's the best place to reach me, and if I'm not available, there are plenty of other talented people around to help. Remember to help support future content and keep these videos free, hit the thanks button below, visit the antCGi store, or join the antCGi club. You can also treat me to a coffee at my coffee page. The link is on the screen now and in the description below. Thanks again for watching. This is antCGi signing off, and I will see you on the next one.